Assalamu alaikum, how are everybody? In our video today, I'll explain Chapter 10, Thermodynamics, Section 1, the relation between heat and work. Let's start. We know the law of conservation of energy. Law of conservation of energy states that energy neither be created nor destroyed, but can change from one form to another. Today, we'll study the relation between heat as a form of energy, work, which can be converted into energy, and a third form of energy, which is called internal energy. So we have three forms of energy: heat, work, and internal energy. What's the relation between them? And we know that the internal energy is related to temperature. If the temperature increases, the internal energy also increases. If the temperature decreases, the internal energy also decreases. So we measure the internal energy by measuring the temperature. Now, here is a nail in a piece of wood. When pulling this nail of the piece of wood, and if you touch it, you feel it to become hot. How come? Why the nail becomes hot? Here, due to the friction force between the nail and the piece of wood, heat is, so there is a work done. This work is changed into internal energy. So here the friction force between the nail and the piece of wood does work. This work is changed into internal energy. By the way, internal energy takes the symbol U, and heat Q, work W, internal energy U. So the work done by the friction force is converted into internal energy. This internal energy causes a change in temperature or increase in temperature, so the temperature increases. So here, work is converted into internal energy, and the internal energy increases, so the temperature also increases. So here is a change of work into internal energy. So the work can be converted into internal energy. Can the internal energy convert into work? Let's discuss this example. Before discussing this example, we'll mention the meaning of a system. What's a system? A system is a group of components. A group of components, or a set of components. So internal energy, system a set of interacting components or particles. a set of interacting components distinct from the surrounding. Distinct from the surrounding. And the system may be closed system, maybe open system, and maybe isolated. So this system is isolated system. What's the difference between the closed and open and isolated? In the open system, matter and energy can be exchanged. A hot cup of tea, okay, opened, so some particles of water can evaporate, can escape. So here matter can be transferred or exchanged with the environment. Environment means the surrounding. And also some energy. The hot cup of tea after some time becomes cold because heat is transferred from the hot cup of tea to the surrounding. Closed allows only energy to escape. So here allows matter and energy, here allows also only energy. Matter not allowed. So the closed system. Isolated, here nothing escape, matter or energy. Here only energy, here matter and energy, here no matter, no energy can escape this isolated system. Let's explain an example for exchanging between internal energy and work. Here, a flask. This flask containing an amount of water. And this flask is heated, and here is a balloon attached to the flask. When the water is heated, it starts to evaporate. At the boiling point, the vapor particles here start to fill the balloon and press on the balloon outside, so the balloon expands. So here the internal energy of the water increases. This internal energy is transferred to these particles of vapor. So the water vapor exerts a work on the walls of the balloon, so the balloon will expand. So this means that a work is done on the air outside or the surrounding. So here the internal energy of the water vapor is changed into work done on the surrounding or the outside world. So its internal energy also decreases and it becomes water drops again and falls down. So here in this example, internal energy is converted into work. The internal energy of the water vapor is changed into work. So here we have the internal energy that can be changed by what? First, by heat. If heat is added here, so the internal energy increases. So heat added or removed. If heat is added, the internal energy increases. If heat is removed, the internal energy decreases. So the internal energy can be changed by heat and can be changed by work done. If the work is done on the gas, its internal energy increases. A work is done by the gas, its internal energy will decrease. So here is a relation between internal energy, heat and work. And heat and work are forms of energy that can be transferred to the system to increase what? The internal energy. So the stored energy inside the system is the internal energy. This internal energy can be changed, by heat or work. Now we find the work done on or by a gas. Here we have a gas, this gas in a container. This container has a cylinder, movable cylinder that can move up or down. The volume of the gas, V1, and this volume increases by this amount to reach this height. The distance moved by the piston equals D. We know that the pressure equals force over area, and the increase in volume here, which is delta V, the change in volume from V1 to V2 equals A multiplied by D, cross-section area multiplied by the height moved or the distance moved. Now we know that the work is the force multiplied by distance. Let's substitute here force. Let's multiply first by A over A. Here is area. Area over area equals 1, multiplying by 1, nothing change. So let's modify F over A, F over A multiplied by A times D. Nothing changed at all because we multiplied by a quantity and divided by the same quantity. F over A represents the pressure. A times D represents the change in volume. So the work done on or by a gas equals the pressure multiplied by the change in volume. Work equals pressure multiplied by the change in volume. Here the pressure must be constant, at constant pressure. So the total work done on or by the gas equals pressure of the gas multiplied by the change in volume. If the pressure equals 0, the work equals 0. If the change in volume equals 0, then the work will be 0. If the volume of the gas doesn't change, nothing happened. Nothing happened. Here, the gas here, the piston doesn't change. No change in volume. As no change in volume, delta V will be 0 and no work is done. Now let's discuss an example. The volume V1 equals 0.2 meter cube, and the gas volume it changed into V2, which is 0.25 meter cube. and the pressure equals 1 times 10 power 5 Pascal or Newton over meter square. Find the work done. Find the work done in this case. So the work done equals first of all work equals P delta V, or the change in volume. First we find the change in volume delta V. We have V1 and V2. So delta V equals V2 minus V1 equals 0.25 minus 0.2 equals 0.05 meter cube. This is the change in volume. Now the work equals P delta V. P equals 1 times 10 power 5 Newton over meter square times 0.05 equals 5 times 10 power 3 joules. You notice that the work here is positive because V1 is larger than V2 is larger than V1. Another example. V1 equals 0.2 meter squared. V2 equals 0.15 meter cube, and the pressure equals 1 times 10 power 5 Newton over meter squared. What's the work done in this case? So let's find first the change in volume. Delta V equals V2 minus V1. Always the change equals the final minus initial. And V here is capital because it's volume, not velocity. 0.15 minus 0.2 equals negative 0.05. The work equals P delta V. The pressure 1 times 10 power 1 over 5 Newton per meter square multiplied by negative 0.05. Here the work will be negative 5 times 10 power 3 joules. The work here is negative. So the work can be positive or can be negative. When the gas expands, the gas expands, so the work is done by the gas. Work done by the gas, and the work here will be positive. If the gas contracts or decreases in size or compressed, the gas is compressed. So work is done on the gas, and in this case the work will be negative. So the work can be positive or the work can be negative depending on the gas expands or the work is done by the gas, it will be positive. If the gas is compressed, the work is done on the gas and the work will be negative. Another example. Here we have a container containing gas, and this container is provided with a piston, movable piston that can move up or down. Here is the gas. The area here is 0.5 meters squared. This is the cross-section area. And the piston moved up a distance 10 centimeters. The pressure equals 1 times 10 power 5 Newton over meter squared. The pressure here is kept constant. Find the work done in this case. Find the work done in this case. What's the work done here? The piston moved up 10 centimeters. The area equals 0.5 meters squared. First, we should find the change in volume. Delta V equals A times D, area multiplied by the distance moved, this distance. This is the change in volume. The change in volume equals the distance multiplied by the area. So 0.5 meters squared multiplied by 10 centimeter should be converted into meter, 0.1 meter. So the change in volume will be 0.05 meter cube. This is a change in volume. Now, to find the work, equal P delta V. The pressure 1 times 10 power 5 Newton over meter squared multiplied by 0.05 meter cube. So the work done equals 5 times 10 power 3 joule, and the work done here is positive because the volume here increases. Thermodynamic processes. Thermodynamic processes. We discussed three forms of energy: heat, work, and internal energy. Heat, work, and internal energy. The exchange between the three forms of energy is called thermodynamic. So thermodynamic, the branch of physics that deals with the exchange between the work, heat, and internal energy. This exchange can take place in different ways. So we have different thermodynamic processes. The first process is called isovolumetric. Isovolumetric process. The second is called isothermal, and the third is called adiabatic. So isovolumetric, isothermal, and adiabatic. What's the difference between them? What's the difference between the three processes? Isovolumetric here means constant volume. Volume is constant, no change in volume. So constant volume process is called isovolumetric. Isothermal means constant temperature. So isothermal means constant temperature. Adiabatic means thermally insulated. Thermally insulated. Here, constant volume, and we discussed that the work equals P delta V. Constant volume means delta V equals 0. So the work done in this case equals 0. Constant temperature, no change in temperature, delta T equals 0. As the change in temperature equals 0, the change in internal energy equals 0. No change in internal energy. Thermally isolated, no, means no heat is taken or given by the system. So Q equals 0. So on the three processes, in the first one, the work equals 0, isovolumetric. Isothermal, the change in internal energy equals 0, no change in internal energy. And here, no heat given or taken by the system. Okay? So, in the isovolumetric, heat can change into internal energy, and the internal energy can change into heat. So there is exchange between the heat is given, can increase the internal energy. If heat is taken, decrease the internal energy. So the change in internal energy because of heat taken or given to the system. So heat is a change into internal energy. And the constant temperature or isothermal, delta U equals 0. So work and the heat can be exchanged. Heat can be changed into work, and work can be exchanged into heat. Adiabatic means Q equals 0, means that there is an exchange between work and internal energy. The work done on a system can change into internal energy, can change the internal energy, and also the internal energy can be changed into work. So there is the three thermodynamic processes, and no thermodynamic process is pure. Means sometimes we can neglect the work, sometimes we can neglect the change in temperature, sometimes we can neglect the change in heat. But for example, in the isovolumetric, some work can be done, but we can neglect it. In isothermal process, some change in internal energy can happen, but we can neglect it, small. Here, in adiabatic process, some heat can be taken or given by the system, but it's very small, so we can neglect it. So these are the thermodynamic processes: isovolumetric, isothermal, and adiabatic process.